In the previous 4 lectures, we talked about the first law of thermodynamics, and here in lecture 5 and for the next few lectures, we're going to be talking about the second law of thermodynamics. We're going to start out talking about the second law by using the example of heat engines. There are a couple ways to go. The way we did it in introductory chemistry was to talk about molecules, the statistical distribution of molecules, and so on. And that's one way to do it. But in fact, thermodynamics rests not on the molecular theory. In fact, if tomorrow the theory of molecules, if somebody proved that there were no atoms and molecules, then thermodynamics would still be okay. So we're going to start not talking about atoms and molecules like we did in introductory chemistry and talking about the second law and entropy. Instead, we're going to start talking about heat engines and Carnot heat engines and the Carnot cycle. That's the way most physical chemistry textbooks do it. All right, let's talk, say a few words about the second law of thermodynamics. There, as you probably know, there's things that are like spontaneous. They seem to happen with no urging whatsoever. Let's talk about a couple of those. Let's talk about this situation. Suppose you have a metal block. This is some sort of metal, and this has a high temperature. And let's take another metal block. Same metal block, but this is a low temperature. Now let's bring these two blocks together so they're now touching, and so there can be some thermal contact between the two. And this is high temperature, and this is low temperature. Okay, so we just brought those two metal blocks together. What's going to happen? Well, every time you do this in the history of humans, every time you do this experiment, take a high temperature block and put it into a low temperature block, what happens is the high temperature block cools and the low temperature block heats up. In other words, heat is transferred from the high temperature to low temperature. It never goes the other way. Never have we ever seen that the high temperature block of metal gets hotter and the low temperature block gets lower. Now this would, if that process were to occur, namely heat would flow from low temperature to high temperature, that would still be within the realm of the first law of thermodynamics. The first law would not be validated. But on the other hand, invalidated. That's still consistent with the first law. But we never see that happen. So this seems to indicate that there is a need for perhaps a second law of thermodynamics. Let's take another example here. Here we have a collection of gas molecules, and here we have another collection of gas molecules. Let's make this helium here, and make this argon here. And this is a partition here. Let's remove the partition. What happens when you remove the partition? Well, now we just have a single container. Oh, he has helium, 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 argon here, helium, argon, argon, so on. What I'm trying to say is what happens if these gases mix? They mix like this. Never ever do you see given a collection of helium and argon atoms, never ever do you see all the helium atoms go to one side and all the argons go to another. You never see that. So this is like a spontaneous process. It always happens. It always goes in one direction. This is a spontaneous process. It always happens. It always goes in one direction. For instance, here, I mean, there's no violation of the first law of thermodynamics, just to have all the helium in one and the argon in another, but it never happens. So what I'm getting around to saying is that we need another law, and that law is going to be called the second law of thermodynamics, to predict the direction of spontaneity, things that just happen that don't appear to violate the first law, but they always go one direction and they don't go the other. All right, now as I said, most physical chemistry textbooks and courses start out talking about heat engines, and we're going to do the same here. So here's a general diagram of what I mean by a heat engine. We have a high temperature reservoir over here. We have a low temperature reservoir over here. And what happens is that some heat is transferred from the hot reservoir into the heat engine. The heat engine does some work on the surroundings, and some additional heat is then transferred from the heat engine to the low temperature reservoir. So some heat flows into here, the engine does some work, and then some excess heat flows out here to the low temperature reservoir. All right, so that's a general diagram. What we're going to talk about in demonstration in class is a kind of heat engine called the Stirling engine. It's not the one we'll talk about in more detail later in this lecture. We're just giving an example of the Stirling engine, and I'll go over this in more detail here. There's an engine, a piston going up and down, turning a wheel up here, and so on. If you want to know more about this, you can read this Wikipedia article and then come to class on Friday, and I have a demonstration of that. That's the Stirling engine. Actually, you can actually buy and make Stirling engines. All right, and the idea is that a heat engine, it operates between two reservoirs of one hot temperature, one low temperature, and heat flows from the hot through the engine to the low. All right, now let's talk about a particular kind of engine called the Carnot heat engine, named after a French, I think it was French scientist in the early 1800s who looked at this kind of heat engine and looked at thermodynamics of it. If you have the textbook ball, it's in figure 3.1. If you have another textbook, you can see a heat engine, and here's one I pulled off the internet. You can check this out here if you're interested in doing it yourself. So there's a picture of Carnot, French scientist, and this is the cycle here. Okay, I'll just give you what this is going to look like here. So the engine goes, heat is transferred, pistons push back, turning this wheel, and then whatever this fluid is, we're going to consider an ideal gas, and it's compressed, the wheel still turns, and so on. All right, so that's what we're looking at. So the Carnot is, the engine is a system. So when we look at heat and work, we're considering the engine as a system, and that heat going into the engine will be positive, work done by the engine on the surroundings will be negative, and so on. And the heat transferred to and from the engine to do work on the surroundings. And in the Carnot heat engine, this is a perfect engine. There's no friction whatsoever. So all these things are frictionless, and so really we're getting the absolute positive best engine we can. We're just making this a frictionless piston. The idea of the Carnot cycle, which we just saw in the previous slide, is the Carnot cycle, and it goes up and down, consists of combinations of reversible expansion and contraction of ideal gas. So remember when we said reversible, you get the most work done out of a system when you go from the initial to final state by a reversible process. So the Carnot cycle will give us what we're looking at as efficiency, which we'll define in a minute. It gives us the best efficiency possible in taking some heat from a reservoir and making the engine do some work. So we're doing a reversible expansion contraction. That will give us the most work, and also we have a perfect engine, no friction. All right, so there's the heat engine we just saw. If you want, you can go to this website to run this little flash animation if you want by yourself. All right, here are the 4 steps of the Carnot cycle. The first is a reversible isothermal expansion. Well, let's see if we can restart this. Okay, so here we go. So this is a isothermal expansion, meaning we have the hot reservoir, so we have 2 heat reservoirs. Here's the hot, and it's transferring heat into here to maintain this at a constant temperature and pushing the piston back. Okay, so that's the first step right there. Now the second step is a reversible. All these are reversible. A reversible adiabatic expansion. Now remember, adiabatic expansion means there's no heat transferred into the system. So now we have an insulator here. The gas is still expanding. There it is. And now we've expanded the gas. The third step is the reversible isothermal compression. So now what we're going to do is to switch out this insulator into the low temperature reservoir and suck some heat out. So now what we have, this is isothermal. Now heat is flowing out of this into the low temperature reservoir, and the thing is compressing down like that. And then finally, the fourth step is reversible adiabatic compression. So on this fourth step, what's happening is that we're changing this low temperature reservoir to an insulator. So now we have insulator, and now we compress the gas here adiabatically. Okay, let's look at that again. So now we have high temperature. In this case, it's 600 Celsius, actually 600 Kelvin it looks like. High temperature is isothermal. This block is 600 Kelvin. We're putting in some heat in there. There we go. And now we have the adiabatic expansion. Remember, adiabatic, expanding a gas, the temperature of the gas is going to drop. So now the temperature goes down. And when it gets to that low point right there, we switch out the insulator and put in the low temperature reservoir, which is equal to 300 K, the temperature of the gas at that point. We suck some heat out. It's isothermal. That third step is isothermal. And then finally, here we're going to switch again to the adiabatic, replace this with an insulator. And now the temperature goes up because we're compressing the gas adiabatically. Expand isothermally, expand adiabatically, compress isothermally, isothermal compression, and then finally we will compress adiabatically, temperature changes. Alright, so that's the Carnot cycle. And we're going to look at this thermodynamically. We already know how to calculate energy changes for isothermal and adiabatic expansion from our lectures in, I believe that was part 4, lecture 4. So let's look at this. Now, this is a cycle. So this is a pressure volume diagram. You're starting up here, goes down here, goes up there, and you end up there. So since the cycle, if we look at it, one Carnot cycle, the change in internal energy is 0. And the change in internal energy is the heat transferred to the system in this step, that step, that step, and that step. Each one of those 4 steps, there's some heat transfer to the system, and there's also some work done on or by the system. 1, 2, 3, 4, those are the 4 steps. And that's equal to 0. Okay, let's look in more detail this pressure volume graph for the Carnot cycle. Again, isothermal, adiabatic, isothermal, adiabatic. Okay. Now, we'll do a pressure volume graph. I remember from isothermal, the relationship between P and V is like P1 V1 is equal to P2 V2. And remember for adiabatic, it was P1 V1 raised to the gamma power is equal to P2 V2 raised to the gamma power, where gamma, remember, was the ratio of heat capacity at constant pressure over heat capacity at constant volume. So that means that for the isothermal, we're going to start right up here. Let's say this is point A. This is just PV. Now, when we switch from isothermal to adiabatic to make this point B, we see that since gamma is greater than 1, In other words, the heat capacity at constant pressure is greater than the heat capacity at constant volume. That means that P will decrease faster than you expect because now the x-axis here is being raised to a power. So now instead of keep going down there, it'll go a little faster. This is point C. This is the first, this is the second step. The third step is isothermal. So again, you're having this relationship. PV is a constant here, goes up like this to point D. And then finally, adiabatic, again, you get a bigger dependence of P on V, goes something like this. All right, so that's supposed to look like this graph here. All right, so we understand that. All right, so that's the pressure volume work. Pressure volume. Now let's see what kind of work can be done here. Well, maybe it's obvious that the amount of work done is the area inside this PV curve. So recall that in the first case, when you have expansion, the system is doing work on the surroundings. There's that under here. And then when the system is contracting, this is doing work on the system. The surroundings doing work on the system. So that's that. So you have to subtract these two. So the work done is just the area in this curve. All right. So that's just an application of what we learned in the second and third lectures, or third and fourth lectures maybe, to this particular lecture, lecture 5. All right. So let's go back here. So let's look at this thermodynamically. Since steps 2 and 4 are adiabatic, that means that Q2 and Q4, there's no heat transferred in the second and fourth steps. So that the total Q total, the total heat transferred, is the heat transferred in the first step, isothermal, plus the heat transferred in the third step, isothermal, and the second and fourth are adiabatic. Let's look at the total work. Well, you're doing work on or by the system in both steps, the expansion in both isothermal and adiabatic, you're doing work here, and the compression. So the work term, the total work, has 4 terms. Work done the first step, second step, third step, plus fourth step. All right. Let me check my notes here, see where I'm going. Oh yeah. Now, since the change in internal energy U is 0, this implies that the minus the total work, the work total is equal to the total heat transferred, because remember when delta U is 0, the internal energy change is 0, minus W equal Q. So it's just equal to Q1 plus Q3. Note that, let's look at this. This total work done will be less than 0. In other words, the work done, if you actually look at, the total work done, well, the PV, this area is a positive number, but remember the work goes as minus PdV, so dW is minus, so don't forget that minus sign. So even though the area is positive, the work is negative. But when you put that negative sign in front of it, this total term here has to be greater than 0. So Q1 plus Q3 has to be greater than 0. Now we know that for Q1, for that expansion, okay, for this expansion, heat is flowing into the hot gas. So Q1 is greater than 0. For that first step, heat is flowing into the system, into the engine, so Q is greater than 0. And we know that Q3 is less than 0. Q3 is less than 0 because now heat is flowing no heat flowing in and out. Now heat is flowing from the cool gas to the cool reservoir, so the system is losing energy. So for that third step, Q is less than 0. All right, so what we have is on the left-hand side, you want a number greater than 0. On the right-hand side, you have two numbers. One is greater than 0, one is less than 0. In order to get this term greater than 0, Q1, the positive number, has to be bigger than Q3, the negative number. So this implies that Q1 is greater than Q3. So how much heat you put into the engine is more on an absolute scale. Let me just say this way. Let me put absolute values around here so make sure we know what I'm talking about. So the absolute value of Q1 is greater than the absolute value of Q3. So the amount of heat you put into the system has to be more than the amount of heat you take out of the system. And that sort of makes sense because you're doing work, and that's why the heats are not equal. Put some heat in the system, some of that heat is converted into work, and then some of the heat goes out into the cold temperature reservoir. Okay, so we've looked at the Carnot cycle thermodynamically. Now, back then, the engineers were interested in efficiency, how to get the most bang for the buck, so to speak. So they defined efficiency of an engine, or a heat engine in particular, as the energy you get out divided by the energy you put in. And if the energy, or if you have a 100% efficient engine, then all the energy you put out is all the energy you put in is equal to the energy that the machine does, the engine does. So the efficiency of 1 will mean all the energy in, you get all the energy out as work. Now, the efficiency of a Carnot heat engine that we're talking about, let's define that as the work we get out of the engine divided by the heat we put in the engine. Okay? Now, there's no reason why, from the first law, that this efficiency cannot be equal to 1. Okay? But what we'll find is that never ever in human experience has one been able to completely get 100% of the work out for the heat you put in. If you put 100 joules in, nobody ever has seen that you'll get 100 joules of work out of a heat engine. So from experience, we find that we never can make a 100% efficient heat engine, even though it is consistent with the first law, so therefore there must be a second law of thermodynamics. And again, this comes from our experience, our collective human experience. We never have been able to 100% convert heat into work. So we need a second law. All right, so let's see if we can get this expression for the efficiency of a heat engine. All right, so we're going to define the efficiency of a Carnot engine as the work we get out over the heat we put in. All right, so the work we put in, we're going to have to use a minus W total. I'll explain that in just a second. And the heat we put in on the Carnot cycle is that heat we put in on that first step when we transfer some heat from the hot temperature reservoir into the engine. So why this minus? Well, remember, engineers are interested in the work you can get out of a system. So they're interested in, like if you do 100 joules of work, they want that to be a positive number. But the way we set up our sign convention is that if the engine does work on the surroundings, then that's a negative number, because the engine, the system, is losing energy to the surroundings. So we're going to put a negative sign here in order to make this a positive number, so that our efficiency can be a positive number. And the heat we put in, the system, the engine, is gaining energy, so that'll be a positive number. So this will be a positive number. That's why that negative sign is there. Well, let's see how much energy we put in. Oh, look, minus W total is Q1 plus Q3. All right, the heat transferred in these the isothermal steps, the adiabatic steps, there's none. So that's the total heat put in. The total work done is equal to Q1 plus Q3. This is equal to the minus the total work. So this is equal to Q1 plus Q3 over Q1. Just divide each thing by Q1. This is 1 plus Q3 over Q1. So there's the efficiency of a Carnot heat engine. It's just the heat you put in at the first step divided by, goes into, divided into the heat that comes out on the third step. All right, and we know that the heat we just said, we argued that in fact this absolute number is greater than that one, and we also argued that this is a number greater than 0, but Q3, remember, is less than 0, and Q1 is greater than 0. So this means that Q3 over Q1 is less than 0, which implies that the efficiency is 1 plus a negative number. All right, so the efficiency will always be less unless you can have Q3 equal to 0 or Q1 equal to infinity. That's usually not the case. So you can't transfer an infinite number can't transfer an infinite amount of heat into the system. That will make that efficiency 1, or you can't suck out, or you can't have no heat come out of the system. Q3 can't be 0. So this implies then efficiency is less than 1. All right, so you know you can't get a 100% efficient heat engine. Okay, now so we've shown that. Let's get another form for the efficiency of a heat engine. Where this is the temperature of the low temperature reservoir, the temperature of the high temperature reservoir. All right, so we'll just again analyze this thermodynamically. In step 1, which was isothermal, we can say that the heat transferred in that step 1, Q1, will be equal to minus W1. Remember, isothermal, delta U is equal to 0, so Q is equal to minus W. So that first step, Q is minus W, and the work is just minus nRT, natural log. Let's use VB over VA as the volume at stage B divided by the volume at stage A. Okay, so here we are. We're starting up here, stage A. We'll go to B isothermally. We'll go to C adiabatically. We'll go to D isothermally. We'll go back to A adiabatically. So this is a isothermal expansion, and let's assume that we have an ideal gas. So assume ideal gas. All right, make things easy. All right, so there is the heat transferred, work done, isothermal compression. And what is this? This is the temperature of the high temperature reservoir, TH. Let's look at step 3. Step 3, again, that's an isothermal. So we can use the exact same argument. Q3 will be minus the work done in step 3, and that's minus nRT. But remember, in step 3 we have heat flowing in the low temperature reservoir times the natural log of VD over VC, where end of slideshow. Well, that sucks. Sorry, I'll just pause this for a minute and put on some more slides. All right, here we're back. Got more slides. All right, so this was the isothermal expand or contraction. Actually, we're compressing the gas in step 3. We said that's that. And let me just define what D and C are here. So we have up here, changing color here. So we have volume A, volume B, volume C, and volume D. All right. So this is isothermal. Step 3 is isothermal. So going from C to D, the final volume is the volume at D minus the initial volume at C. Okay. So that's where that comes from. Now, let's look at the adiabatic steps. Now remember in step 2, that's adiabatic. Adiabatic. Remember, I probably from lecture 3 or maybe lecture 4, for an adiabatic compression of a gas, the final temperature over the initial temperature is equal to the final volume over the initial volume raised to this 1 minus gamma, where gamma is the ratio of heat capacities, Cp to Cv. All right, so let's apply that to step 2, the adiabatic expansion. Now in step 2, maybe just touch base here. So let's start. All right, so here, there was the, let's go back here, start. All right, so there's the isothermal, and we're right down here. Now we're going to switch to adiabatic. Okay, so we're starting at a high temperature. That was the temperature. The gas was initially the temperature at the high temperature reservoir, 600. Now and it's at volume VB. And then finally, the gas down here, after the adiabatic expansion, the temperature is at the temperature of the low temperature reservoir at volume VC. And there's the low temperature reservoir right there. So for that second step, adiabatic step here, we have a final volume of VC and a final temperature of the low temperature gas, and the initial temperature was the temperature, high temperature reservoir, and volume VB. That's where this is. So the final temperature is the temperature of the low. Initial temperature was temperature of the high, and that's equal to the final volume, which was, we said, the volume at stage C divided by the volume at stage B raised to the 1 minus gamma power. We do the same analysis for step 3, which is again adiabatic. Step 4, which is adiabatic. We find, well, in step 4, might as well go back up here. So here comes step 3. Got heat flowing. Keep going there. Now the gas is at the temperature, the low temperature reservoir. That's the initial temperature in volume VD, point D. And now at the end of that adiabatic expansion, we have the temperature of the gas to be the high temperature, the temperature of the high temperature reservoir, and the volume being VA. So that's the final, the initial is down here. So with that, the final temperature is the temperature of the high temperature reservoir. Initially we started at low temperature, and the final volume was the volume at A, and the initial volume we started at point D. And again, this is raised to the 1 minus gamma power. All right. So it looks like we can, so where are we going here? Well, just to so we don't lose sight here, what we want to do is to convert. So we derive this expression. Now we want to know something about how efficiency depends upon temperature of high and low temperature reservoirs. All right, so somehow we have to get rid of the Q's and replace them by T's. Look, here's some T's there. There are some Q's. If we can relate VA, VB, VD, VC, take the ratio. There's how we can get a relationship. So let's rearrange. What should we do here? Excuse me. I guess it doesn't really matter. Let's do this one. All right, so let's rearrange this. Let's say this T low over T high. That's equal to VD over VA raised to the 1 minus gamma power. So we have an expression for low to high in terms of VC and VB, and low to high in terms of VD and VA. So let's equate those two. So we can say that, I forgot it already. Let's see. C to B, VC over VB raised to the 1 minus gamma power. Okay. That's equal to D to A raised to the 1 minus. Gamma power. Well, we just take this root 1 minus gamma, so this implies that VC over VB is equal to VD over VA, or in other words, VC over VD is equal to VB over VA. Well, that's useful. Let's take this ratio, Q1. Actually, what do we want here? We want Q3 to Q1. So let's say Q3 to Q1. Okay? So Q3 to Q1, that's equal to nRT, this is T of the low temperature, times the natural log of VB over VA, so VD over VC, minus minus will give us a plus, VD over VC, over nRT times, that's T, the high temperature reservoir, Q1 was a high temperature reservoir, times the natural log of V, let's get this right here, VD over VC. Sorry, we were looking for Q1, VB over VA. All right. Oh, look, things start canceling out here. That goes away. We have that ratio, which is what we wanted here, low to high. But these things don't cancel out. But, aha, look at this. So, oh yeah. So let's, what do you want to substitute in? Take a poll, substitute in for B over A. Yeah, let's do that. This is equal to T low over T high, natural log of VD over VC, natural log of VC over VD, almost there. That's equal to T low over T high, a natural log of VD over VC divided by the natural log of VD over VC with a minus sign in it. Because remember, you switch these, change the minus, times the minus 1. So it's equal to just minus T low over T high. So the ratio of Q3 to Q1 is minus T low over T high. Okay? So 1 plus Q3 over Q1 is equal, and that's what the efficiency is equal to 1 minus T low over T high. All right, so that's what we set out to prove here, 1 minus T low over T high. So this means to get the efficiency equal to 1, what do you have to have? This implies that T low has to equal 0, or T high has to equal infinity. Now, we've never ever seen an efficient, 100% efficient engine where you can convert 100% of the heat you put into an engine into work. So this means that you can never have T equals 0. In other words, T, this in Kelvin, never have absolute 0. And you can never have an infinitely high temperature. So this means the efficiency is E never equal to 1. Okay. This also interesting is that if you increase the difference in temperature between the low and high temperature reservoirs, then you'll have an increase in efficiency. So as for instance, suppose you have this is 100 degrees, 100 Kelvin, and make this a 200 Kelvin. If this engine, you have an efficiency 0.5. Now, if you say make this a higher temperature, say put this to 300 Kelvin, then the efficiency goes to 0.66. So as you start increasing the temperature of the high temperature reservoir or lowering the temperature of the low temperature reservoir, you start increasing the efficiency of the engine. The hotter you can make that heat engine run, the more efficient the heat engine will be. Of course, this is all frictionless reversible processes, so this gives the maximum. That's another interesting point, is that even though we have the best heat engine, in other words, frictionless and reversible, E can never equal 1. There's a fundamental limit on the efficiency you can get out of a heat engine, and that fundamental limit is called the second law of thermodynamics. Okay, so I think we just had one more point here. Oh yes, so this is an important point. Okay, so let's go back and look at the heat engines here. So we have efficiency is 1 plus heat out over heat in, and that's equal to 1 minus T low over T high. These two things are equated so that Q3 over Q1 plus, we'll just put that out, get rid of the ones and so on, plus T low over T high, that's equal to 0. Or in other words, let's multiply both sides of this equation by Q1 over, what do we want to do, get T low. We'll have Q1 divided by T high plus Q3 divided by T low equal 0. So even though heat is well, what does this mean? This means if you go through a cycle, this is how much heat you put in the entire cycle. This is the first step and the third step, and the second and fourth were adiabatic, so mean no heat transferred. This is the total heat put in. That depends on path. But if you divide by the temperature of the reservoir, so this is the first step divided by the temperature you had of the reservoir the first step, and the heat in the third step divided by the temperature you had the third step, you sum those through that cycle, it's equal to 0. So this implies that Q over T is some sort of, if you add things and you get 0, some sort of state function. Okay, that's cool. And maybe you remember from introductory chemistry, entropy defined as Q over T for a reversible process is a state function. All right, so that's just where we're going in the next part of this lecture. And finally, based on thermodynamic efficiency, explain why it is better to run a steam engine with superheated steam, which is hotter than 100 degrees, than with steam at 100 degrees, and make the bad assumption that a steam engine is similar to a Carnot heat engine. All right, well, we just already answered that question here. The idea here is if you have the high temperature reservoir, the higher temperature you can make that high temperature reservoir, the smaller this number will be, and the smaller number you'll be subtracting from 1, and the better efficiency you'll have, efficiency closer to 1. If this goes up, this term goes down, you're subtracting a smaller number from 1, you get a higher efficiency. All right, so that's it for this part of Lecture 4, and we'll talk more about the second law of thermodynamics in the second part of this lecture.